I just wanted to introduce you as somebody who came across our model who's interested in physics and follows the pop sci and maybe has been like a little dissatisfied with some of the spooky explanations, or maybe you're intrigued by them. I don't want to put words in your mouth, but you're somebody who has kind of been here since the start and interested in what's going on. And I personally learn best through conversation. So I was thinking it would be cool to just do a little podcast for the Material Atomics channel where we sit down and kind of ask me anything. Like, let's talk about the model. Let's talk about scenarios that might not be clear to you as somebody who's maybe seen a few of our videos. You get kind of the basic idea of what we're proposing, but maybe you have questions about some of the details, and I hope we have answers for them. And if we don't, that'll be cool too, because that's exactly what we should be investigating. So yeah, welcome to Material Atomics, and thank you for coming out and picking our brains about this model so people can learn more.
Thank you for trusting me with doing this as well. I'm really excited to dig in. And, I told you I kind of want to make this a friendly challenge. I want to be at times a little bit adversarial, right? Because if I'm just like, oh, yeah, great idea, I'm sure it's going to be fine. As like, there's no value in that. I think really if you test the boundaries of that system, then you can really filter out what's good and, well, what's maybe needs more work, or maybe what's plain out wrong and not so good, right?
Absolutely.
But that said, I have thought about your model for it's been over a year now, year maybe two, I don't know. But I've really been intrigued by it, and I see the value and just a new path for exploring quantum mechanics. Where there are the most open questions in quantum mechanics. How does all this stuff work? Where does the spookiness come from? And I think you guys have an innovative approach to resolving some of these questions, and then also still opening up potential for new discoveries and new ideas that we can then bring to engineering, and who knows what we can make from it.
Yeah, but I mean, please be as adversarial as possible. Like, we firmly believe that science is a progressive art, that theories need to change as new information comes to light. And, we've been working on this model for maybe 5 years, but we just as recently as this summer completely revisited some of the fundamental aspects of what we were thinking light meant in terms of the model. And we changed our mind about a lot of that, and that's important. And so anything that we're putting out is just our best idea of how to explain it. And the model has been really useful for addressing all the phenomena that we've come across. But I'm sure that 100 years from now, people will have a better idea. Maybe somebody will take the material atomics framework and come up with a completely different atom. That's great too. But the framework itself, where, the only actors are these material bodies, and you have to explain the atomic phenomena, you have to explain spooky stuff using material actors, is really what we're trying to get across here.
Yeah, I think there's a saying, right? Every model is wrong, and some models are useful, and obviously that would apply here as well. And there are definitely boundaries to that model, but it is useful in many ways, I'm sure. Nonetheless, though, I'd like to actually hear how would you characterize the actual current mainstream understanding of what light is and how light works? I mean, what do most people think right now is light, and how would they describe and explain it?
Yeah, I mean, this is really interesting, and this has kind of led us to our own revisions of light. Light's interesting, right? If you go to, say, Wikipedia and you type in light and you ask what it is, it'll say, well, there's 3 kinds of light, right? Light can come from heated bodies. Light can come from this quantum jumping phenomena, where an electron is excited into a new state and then relaxes and gives off light. And light can be generated in radio waves as well. And this is interesting because fundamentally, the processes are all intertwined. It all is light. It's all electromagnetic radiation. Now, the interesting thing is that, there's this huge historic debate where light obviously exhibited wave-like properties, like interference, that could only be refined and modeled using wave equations. But at the same time, in order to solve the ultraviolet catastrophe, Max Planck had to quantize light into discrete events, right? The photon was born. the quantum of action. So there's been this long-standing crisis, which has essentially been folded into the mix, where light does act as this singular event, which is called a particle. You can describe it as a photon, but at the same time, it acts as in concert as a wave. And the resolution of this has been sort of sidelined by just the acceptance of it as, well, it is so. It does seem that light is contradictory, and there's so much of quantum mechanics that people see these strange behaviors and they say, okay, well, it's just a paradox, accept it, move on. And so our goal has really been to try to integrate those two ways of looking at light into how could light be a wave-like property, a wave-like phenomenon of the atom, and at the same time be occurring in a discrete manner. And of course, the way we've solved that is through these discrete radial structures that connect the atoms to one another through their electron shells. So
there was something really interesting that we came across when we were working on the most recent model of light, which I feel like we should have realized much earlier. But if you go and you look on Wikipedia or any other place, you'll have a little GIF of what light looks like. And the little GIF is that you have this sine wave of an electric field, and you have this 90-degree perpendicular sine wave of a magnetic field. And these two together are the electromagnetic wave that is light. But when you think about what is being drawn versus what is actually being measured, you realize that the measurement that can take place is only a second order readout. And what I mean by that is you're only looking to see what does the incoming light do to the atom at the detector.
Or at the emitter.
Well, no, because your detector is the only place where you're detecting.
Sure.
Right.
I'm just saying there's like two ends of this transaction.
There's two ends. So there's an atom that is the emitter, there's the atom that is the detector, but your machine is never reaching out to touch the photon in mid-flight to be able to say that, okay, this must be what the photon in mid-flight looks like. You can only get a destination-specific readout. And so the current conception of light is this thing that's happening in between these two atoms, but there isn't a sense of real cause and effect. Like, it seems like when people talk about light, they're not thinking about the fact that the only thing that they're measuring is the action at the detector. And so in order for us to get a better understanding of what that process looks like in between, we have to realize that E&M 90-degree orthogonal sine wave diagram is an extrapolation made off of the action of atoms in the detector. Does that make sense?
Yeah, and I guess I could add to that a huge revelation for us was realizing that actually radio antennas are a great way of understanding what's happening at the atoms themselves. Mm-hmm. Because we have fantastic engineering diagrams of radio antenna, and when you realize that all light is essentially an antenna relay situation, then you can start to pick apart what the atoms might be actually doing. Because in a radio antenna that's, let's say, transmitting light, transmitting radio waves, what's happening is you have an oscillating electric field. It's changing polarity, and the wavelength of that radio wave depends upon the dimensions of that antenna. So what you're essentially saying is that the light is being generated by flipping the polarity of those atoms every single wavelength, essentially. And if you start to realize that atoms themselves are like tiny little antennae themselves, then you get a real picture of what process, what tensions are being applied from one atom to the next during light. And of course, this requires you to have a material understanding of electricity, which is, one of the first things that we played with. And of course, under our model, electricity has to do with the way that that electron shell is moving. It's rotating and it's involuting, and we know this from the spin 1/2 symmetry of the electron. At least we've solved it in one way. It's not maybe not a knowledge base, but it is a way of modeling what the shell could be doing. And so from that, we get this idea that during light, the atom is moving back and forth. The polarity is changing. Its direction of rotation is changing from the positive to the negative in each wavelength of light. And from that, assuming that there's these discrete structures connecting the atoms, we can imagine finally what sort of tensions are being applied to those connecting structures. And we can see how you come to believe that there's this changing electromagnetic field, because in effect, the oscillation of, well, magnetism, of course, following at 90 degrees from electricity, we can see that by oscillating the electric tension upon the surface of the atom, you also are going to oscillate the magnetic direction. And so, kind of what we're trying to do here is take all of this mainstream knowledge and synthesize it into something that's visualizable and that could have material relevance in terms of what the actors might be doing. And in some sense, the entire project is founded on a hypothesis, which is that, hey, there are material actors that are responsible for this. We start with that. And this art of hypothesis-driven research is kind of been sidelined in modern times. It's very hard to publish a hypothesis without substantiating it in some way. In other words, having tested it. But we're talking about actors that are far, far smaller than the instruments that we have today are capable of probing.
I would actually, to wrap this very, very long answer to a very, very, what is a straightforward question?
Well, I told Oliver we'd do most of the talking today, so that he didn't have to. he didn't have to, lean on expertise or something.
Sure. I think that it's just important to realize that this is not a new theory. Right. So Shiloh's like, everybody's always asking, like, well, can you test it? Are you making predictions? And at some point you do have to make predictions, but the testing has already been done. We're basing everything that we're doing off of the math of quantum mechanics and the math of general relativity and the math that has been established by the relativists and the particle physicists, because they have really expensive detectors. They have really expensive laboratories. They've done the work. This is a metaphysical question of how do you interpret the mathematics? And so that is to say that right now the conception of light is very mathematical. It's probabilistic. It is something that behaves one way, it behaves another way. It's this nebulous cloud thing that somehow escapes atoms and just radiates out into space. And we're like, okay, hold on a second. What if we actually thought about this in terms of physical bodies? And so we take the abstract idea of light and we physicalize it.
Yeah, it's if anything that we're doing is revolutionary, it's addressing a new framework for approaching all of the data that we have. We're not trying to say that any of it's, wrong necessarily. I'm sure some of it will be updated over time, but primarily we're just trying to fit it onto a new framework, which is these material actors accomplishing the feats. And honestly, that's something that people were quite on board with until the 20th century, when the mathematicians took over the asylum. And they've been very productive technologically. It's been a fantastic century of technological progress because you don't need that material conception to build things. It's absolutely sufficient to parameterize it into equations and tweak variables and change the designs of your inventions to accommodate what works and what doesn't. But the basic science has kind of been left in the dust along the way. And all of the people from the 19th century that were really interested in solving the material problems of light, gravity, magnetism, electricity, they were, that's sort of thought of as an antiquated pursuit at this point. And we're saying, no, it's actually quite useful. It's not that these are unsolvable problems. It's just that we haven't solved them yet. And here's one idea of how it could be done. Here's the structure that could accomplish that. I don't know if it's right or wrong, but it would work. maybe you have a better idea, but we should at least be thinking about how this could be a useful way of approaching physics, approaching fundamental physics.
Right. And I definitely don't want to get too much into the whole metaphysical concept of that this time, because I feel like we covered some grounds on that last time as well. I definitely see that from my understanding, there is a lack of a unifying theory of both general relativity and quantum mechanics, right? Everybody is aware of that. And of course, there's people developing theories and trying out things. And well, also this goes into a theory of quantum gravity, I guess. And exactly like you were saying, like theoretical research compared to empirical research, there is a difference. And yeah, at some point you have to kind of make this hypothesis that always will be subject to the problem of induction, where you can't use science to prove science. So at some point you're just going to have to be creative and make something up. And if it works with what we observe in nature, then, well, why not? Whatever you made up, somebody made up atoms. That was 2,000 years ago, but we've kind of ran with it and it still works. But anyway, I'd like to, so after you have really characterized well that there are many open questions in what light is, but most people kind of have been taught light is photons, and photons are emitted from atoms. And well, they kind of travel from one atom to another. And what you say about the atoms needing to receive those photons kind of makes sense also. But yes, of course, there is this whole paradox with the wave or particle dilemma, which then leads us to quantum mechanics. But in a nutshell, how would you summarize, I also want to say that you have actually anticipated many of my questions already. I want to kind of make sure we get some clear answers on those. But how would you, in a nutshell, clearly and concisely and briefly summarize your approach and your model of how light works and what it is according to your model? Now that we have clarified, most people think photons and wave particle. What do you think?
I think the slit interference might be a good way to...
Oh, hold on. Like, there's a single sentence answer to this.
Please, yeah.
Light is a communication between atoms that occurs in the filamentary interconnection that lies between all atoms. That's a single sentence, brief summary, and I think that you can probably ask various questions to elaborate on that, and I think that Shiloh's right that the double slit experiment does that, but in its absolute simplest form, the current model of light does not have this handshake exchange between atoms that are connected. It is that there is a little bullet of something that just gets shot out into space, and when it lands on a different atom, that is an exchange of photons. And we're saying that, look, the trajectory of that little bullet, if you want to call it that, which is the wave packet, is predetermined by the network connectivity of the atoms that are within the exchange. And I mean, it's one of those things that you can just keep saying things to add to that, but I think I want to keep it brief to fulfill your...
Yeah, and I would just add that for people who are new to this concept, it's not like we're just pulling this filamentary thing out of a hat. The fact of the matter is that the electron, the surface of the atom, the outer surface of the atom, does seem to fall off. If you try to pick where that electron is going to be found with respect to the distance from the nucleus of the atom, what you're going to find is that you usually find it pretty close. And we call that region the shell of the atom. But there is a non-zero chance that you will find that electron, you will be able to touch it at any distance from the atom. And we're saying that's not spooky or weird. That means that some portion of the surface of the atom is very rarefied after that shell distance. And that means that we have a material for interactions like light and gravity to occur in, and we say, hey, not only is it rarefied, but it can hold tension, and it appears to be a straight rectilinear path between atoms because of the ray nature of light. And from this, we pull out, hey, I think that this rarefied electron material is organized into a structure that we call a filament, which is essentially this long, connected connective tissue between the atoms, which is made up of the atom, the same material that the atoms are made of. So it's not just something that we made up because it works. We made it up because it's a concise way of describing what the data actually says is happening. And so, like Nastia said, light in its simplest form is some sort of material, an actual tension, some sort of tension that's occurring in this structure, which is transmitting opposing forces to the surface of the atom, which can then lead to all of these different interference behaviors, which we can get into if you want.
You use a lot of kind of big words here, or words that maybe require some more definition, and you did define some of them. Really, the new idea that I took away from it was the idea of filaments, right? And by that you mean that atoms are sort of connected with, well, something that enables the communication, and the photon, what we think of the photon right now, actually propagates among that sort of straight line thing between two atoms. Is that right?
That's absolutely right. Yeah. Yeah, the photon is an activity, actually. That's the big change here, is that mathematical physics doesn't have a way of distinguishing between bodies and activities. And so a particle in mathematical physics can really be some aspects of either mixed together. And the photon, because of the fact that it has momentum, it's a motive thing. It's in action. It's a dynamic event. We're saying that's actually an event inside of a structure. Structures have been sort of sidelined over the last century. Nobody's really concerned with what the structures are because they have these very dynamic ways of describing the activity. They call them fields. And when they instantiate those fields and they say, aha, right here, what's happening in the field right here? Well, that's the particle. And we're like, that's where you're measuring what's happening inside of these structures. And the field is the sum total of all of those events and all of those predicted events.
And so, like you said earlier, your hypothesis that all of this underlies is that there is some type of ether-like material even between the atoms still that exists, but it can't really be detected, which then, of course, is kind of weird to go deeper down there. But if we can use that to build a model that works, then why not, right?
Well, so the difference between a traditional ether model and what we're doing is, I think, the difference of disunity. So in a traditional ether model, you have substance, and then things float in that substance. Atoms, bodies, planets, whatever, everything floats in the substance of the ether. The ether is what fills the gaps in between the stuff. But in our model, the stuff and the bodies is the same thing. And so it's an interconnection, but not a interconnection. It's not a two-body system, I guess, right?
It's not a separate substance.
It's not a separate substance. And so when you're looking at something like ether drag, you're looking to see how the body of the planet drags as it moves through the ether of space. But if the body of the planet and the ether of space are made of the same stuff regionally, right? This changes as you start to go farther and farther out. It's much harder to detect that, and you have to design probably a smarter and more clever experiment to see it. Like, you might have to have your detectors farther away from each other. You might have to... It's a very difficult challenge.
Just to clarify, because the atom under our model is radially organized, when an atom moves, it drags its filaments with it necessarily, right? So this really complicates any attempts at externally detecting those. If you treat them as they should be a static substance that's just in the background, they are not a static substance. They're rearranging with the atoms as they move. I personally think you have no chance of detecting them with any of these drift experiments because of that. But if you were, there is some evidence, though, of ways to detect them. We did a little video on the Shapiro delay phenomenon. I think there is some hints at, because of course these filaments are transecting each other constantly, and that's a whole nother issue we can get into, but there's some evidence for that phenomenon as it happens in large agglomerations of atoms. and you can see some effects that hint at how that transection process, in other words, the filaments do show up in certain little ways, and we can get into that. But
I think this is just a sore point, because when you start talking about the ether, there's good reasons to have thrown out the ether. And this is something that we have to always be talking about, because in some ways this is an ether-like model. And in order to justify an ether-like model, you have to address the good reasons for having thrown out the static ether in the first place.
Like, I toyed with the idea of calling it structured ether at some point. Sort of like how structured water is kind of a really cool topic, because everybody thinks of water as just this sea of little water particles floating around, but in reality there's all of these actual tensions being applied, and it can form these units that are capable of doing work under different situations of tension and confinement and so forth. And in a sense, what we've done is we've said, hey, it's not just a sea of chaos. There's actually structure among these fibers of existence, these pieces of ether, and the structures can be informed by the data from the experiments. We can actually get a picture of the structure of this ether. It's not just a chaotic sea of madness that does magical things.
There's not on my list of questions here, but that's kind of your backstory too from that, right? You did your PhD, which is, well, no, wait, your PhD is separate from the thing that was published in Nature, but that's all got to do with somehow the dynamics of water and really the atomic and molecular stuff that's going on, right?
Yeah, man, that's kind of how I got into all this too. And honestly, the tool that I use, the atomic force microscope, in particular, my lab had this, our lab head, Özgür Şahin, had developed a very unique way of using the atomic force microscope. And without getting too lost in the details of that, he basically had a torsional aspect to it, where in a traditional AFM, you vibrate a cantilever, you can scan surfaces with it by reflecting a laser off the top to amplify the little changes in height that you might experience. And Özgür realized you could get more information by adding torsional processes to it. And I realized that a lot of the maths that were describing these torsional processes were very similar to the oscillatory behavior of light as well. And in general, a lot of the, like when we're doing AFM, it's all elastic mechanics. The way that something behaves in terms of its stiffness and it's basically the way it flexes and gives, all of these equations are very, very congruent with much of fundamental physics. The atom seems to behave as an elastic harmonic oscillator in many cases, light being one of them, electricity and magnetism in general. And so there's so much overlap there. And having just looked at systems for years in that laboratory as elastic processes, it just became increasingly clear to me that that was what was happening with the atom too.
I think that's a key part that's really important for people to realize as well, because I know oftentimes there's kind of the whole issue of who are you person on the internet to tell us how reality works. All these textbooks that we've written about our nicely structured atom with the little orbits and whatnot, you're trying to change all of that, but I mean that's literally your job, right? You're a scientist with a PhD who's publishing this stuff, so that really, I mean, adds credibility, to all of that. But let's get back to the pop science. Everybody likes the double slit experiment because it's so nice and spooky. And one of the, like, really, for me personally, one of the first things in physics class where I'm like, what is this? Because I told my mom at home, I remember when I learned it in school, I came home, I told my mom, did you know in physics there's something going on where, like, imagine you bake a cake and you go back and then there's the cake, but it's not what you actually thought the cake was going to be. Like, it turns out to be a chocolate cake, even though the ingredients were for a cheesecake. So now you do the same thing again. You watch the cake bake, and now suddenly it does become a cheesecake. So watching is like an ingredient for the cake. I mean, that's that's my idea of the double slit experiment. How would you kind of characterize the double slit experiment and its significance to your model and everything? How that interconnects? You were just already hinting at it.
Yeah, I mean, I would say that we just, most people don't realize it, but a single slit will interfere also. And it's simpler if we just start with single slit interference.
I want to give a little bit of context before you dive into the details.
You can take it away too.
No. I think it's fine. I think that you have a really good way of handling this, but I just want to give a couple of orienting points so that someone can follow the discussion more easily. Because the watcher is significant, and the chocolate cake turning into a cheesecake is not maybe exactly what we think is happening. So you are in a system where you're purportedly taking photons and sending them through these two slits, and then you get this interference pattern on the background. And you have to ask yourself
about... Or a single slit.
Or a single slit, but I want to talk about the double slit because the observer is part of this, and that's one of the weirdest things for quantum physics, which is like, oh my god, the observer changes the results of the experiment. It's so significant.
Well, and it's double slit single photon. What's significant there as well, right? Because if you just send a sea of photons, you're like, well, okay, they behave like waves, kind of like as if you would shoot water through the two slits. But if you do that with particles, you would not expect an interference pattern. And so then they tested the single photon, like, okay, what happens if we just send one? And the fact that they can't predict where the photon lands on the screen, that's what makes it so weird. But as soon as they look which slit it went through, how can it be that one photon acts as a wave and sort of interferes with itself? As soon as they look, then it's like, oh, I was actually a particle all along. Don't mind me, right?
And I think that a lot of that mystery has to do with the assumption that atoms are reacting to light in the detector in a way that is one for one, right? So if you have a double slit and you're sending photons through one at a time, and then you get this interference pattern, everybody's like, wow, that's so crazy. They came one at a time and they showed up after each other. And so they must be like interfering across time in order to give the pattern. And that's so weird. But it also is possible to say that, okay, well, what if your detector, the screen on which you're projecting the image of the photons, the individual atoms within that detector that are getting hit by the photon they have memory. And so you're developing, because you can't shoot a single photon.
Yeah, hold on. That's what I wanted to say is like, what do they mean when they say they shoot a photon? It's an energy threshold, actually. They're like, this is the energy that we have calculated should be in a single photon.
So that's true. But then in addition, you can't shoot a single photon and then have the interference pattern appear. It's not, your detector is not sensitive enough to be able to get that. You have to be able to shoot multiple photons.
One after another
over a long period of time, and then you develop the picture, right? And so if the atoms in your detector, in that film that's developing the photograph of the arrival of the interference, have memory where they get hit by a photon, and then they need to be hit by a couple more photons to change their color, the scattering of the light of the photons at the double slits will always remain constant because the pattern is a geometrically determined thing, right? So it's not like mysterious what that interference pattern is going to look like based off of the geometry of your system. Two slits with the exact same distance between them, the exact same width, they have a mathematical formula that tells you exactly what your interference pattern is going to look like. Okay, so we have atoms that have memory, that have a threshold that they have to pass in order to show this interference experiment. And so as you're putting these photons through your two slits, they scatter because each one, if you have... Go ahead.
Maybe we should just lay out the basic mechanism for interference before we get too far down the rabbit hole with the threshold model.
Well, hold on. Let me wrap the thought, and then yes. Yeah. So, if you can allow for the fact that there is a time-integrated domain under which the interference pattern appears, then you have one more factor, which is that, okay, if I watch it happen, the watching is an ingredient in the experiment and the interference pattern doesn't happen when I watch. That's crazy. But I think that what that's doing is you watching are stealing energy from the system. You're stealing, because you're detecting something. So you're pulling out motion from the system. And when you pull that motion from the system out, you fall below the threshold level of activating the atoms on the detector. And so you get the two lines because you've stolen something from the system. And when you're not watching, then you have enough energy that's left in the photons in order to generate the expected interference pattern.
Yeah, I would point you towards some of the experiments of Eric Reiter. He's done a lot of work on, I hate the word debunking, but really tearing apart this idea of single photon and what that really means. And, he, without really, he's got a whole channel you can check out, and he does all these awesome garage experiments, and he's got quite an accomplished knowledge base and experimental setup where he's like, look, the way that atoms work is that they need a certain level of kick in order to jump into that next orbital excitation before they can relax and give off anything. And a detection, reflect a piece of light, whatever. They can't do anything unless they get a certain amount of energy. But if you imagine you have a bunch of cups on the table and you say, you fill them like all a little bit full of water, let's say. Some of them are more full than others. Some of them are completely empty. And you say, hey, this Dixie cup over here represents a photon's worth of energy. The water is the analogy for energy here. And you pour that water into all of the cups. Well, some of them are going to overflow, and some of them aren't going to be totally full yet at all. The ones that overflow are going to give you that kick. They're going to give you that reflected photon or that detection event on your chemical reaction, whatever it needed. And so what you're doing is you're adding each one of these single photon shots is really just a burst into the network that's filling up some of the cups, and it's filling up just enough to kick over a statistically significant one of them. And so,
quick interjection, is that what you meant with the photon has memory earlier?
Yeah.
Yeah, when I was saying that the atoms have memory, that's exactly what I was saying.
Atoms have memory, okay.
Mm-hmm.
Yeah, so what you're doing is you're kicking these atoms a little bit, getting them whirled up a little bit. Some of them aren't getting enough to go over into the next orbital so that they can actually relay a signal of light themselves or activate the detector in whatever manner that's being done. And so the thresholding of all of this has to be taken into account. That being the case, we do think that light is happening in a discrete fashion in that it's occurring inside of discrete structures. And
that the geometry of the slits informs the way that it scatters. Yeah,
that seems absolutely apparent. But it seems really important. I'm just worried that we're getting too far away from actually explaining what interference is going on.
I think that this is all important. And I think that we've explained this idea of the threshold. We've explained the idea that the photon is something that is activating the atoms that are on the detector. We've explained that when you start to look at the system, it's not a neutral activity. You're actually taking something from the system. And so now the thing that we have to deal with is, okay, well, what is interference? What is getting scattered? And what are the light versus the dark bands that are actually on the back of that detector? Because it's weirder than it seems. Because what you would expect is not a band pattern of light and dark. If you just have a geometric scattering at the slits, you would expect it to just spray out and to just have this smear of light on the back wall. Right?
Mm.
Yeah, and instead it's almost like you're casting bands of shadow into the light, which is what was so puzzling to people across the ages. You have these dark bands that seem to be reflected into the margins.
And this is where the wave nature of light comes in, because you're not just taking something and like smearing it across the back. You get a pattern that looks like waves interfering, because you have the troughs and you have the crests, and when two troughs meet, you get nothing, and when two crests meet, you get something that is strong. Oh no, sorry. That's not true.
That is my understanding of interference, exactly what you described.
No,
right there.
Two troughs, it should be a crest and a trough. When they meet, you get nothing.
Yeah.
Two troughs, it's like, so right, you have an amplitude, your signal has amplitude, and your amplitude is only 0 when you have a crest and a trough.
Right. So it can be like positive or negative, basically. It can go either way.
Exactly. Exactly.
Exactly. And so what we're adding to this mix with our model of light is we're saying, hey, what's actually happening is that when you have that positive field being experienced,
What's positive field?
yeah, polarity. When the polarity, right, that wave has a polarity that's positive, and it has one
when
that's
it's up, the wave is up high.
yeah, and that has real meaning in terms of what's happening at the atom. Because when it's up high, when the atom is experiencing the high part of the wave, it's receiving a polarity in one direction. That is, its shell is twisting in one direction. When it's negative, it's actually twisting in the opposite direction. So what happens is when an atom receives a positive signal and a negative signal at the same moment, it's being told to turn one way and the exact opposite way at that exact same instant. It does nothing. It receives no kick whatsoever. It can't participate in this threshold business that we've been talking about up to this point.
And it gets dark.
And so because of the fact that these waves have an actual length to them, right? The waves have, it takes some time for that material to experience the change in polarity at the surface of the atom as it's emitting that wave. There is an actual distance relationship with this wave. That is, the wave has, it will, as the geometry changes, as you lengthen the arc between any 2 points in that slit to the screen at the back, you're going to be having areas that are receiving countermanding signals at any given time. And what happens is that, of course, this very traditional wave mechanics takes over where you have peaks and troughs interfering. Everybody knows that. The question is, what the hell is happening where what two signals could be causing a deadening of the receiver atom at the back? And we're saying those are opposite physical tensions which are being applied to the surface of the atom.
I'm not going to lie, but I am a little bit confused, even though I sort of understand your model. So I'm kind of not sure what a viewer might be going through right now. But let me ask you just the simple kind of yes or no question. Could we, in principle, predict where the photon lands on the detector in the double slit single photon experiment with a higher accuracy than what currently the Schrödinger equations give us, which is basically just a probability, right? Schrödinger equations tell us, well, you have a X amount percentage probability where it's going to land. Using your approach in your model, could we somehow time or measure or set up an experiment where we're like, this time it's actually going to be landing on the far end, watch, and then you do it and then it's on the far end, or will it always be kind of random and probabilistic?
I would expect that it would always be probabilistic because we're talking about a network, right? Like you're talking about, you have the emitter of photons, you have the
emitter atoms. Is that what you meant?
The emitter of photons, which is a thing that's made out of atoms, yeah. So you have the emitter of photons, which is a collection of atoms that are being excited in a specific way. You have this wall in which you have your 2 slits, and then you have your detector that is at the back of the experimental setup. So the photons, when they hit the double slit, will scatter through the network of filaments, and the network of filaments is all of the atoms in that vicinity connected to one another. And so I think that you can only really get a probabilistic measurement out of that.
Yeah, I mean, simplest case scenario, just to be absolutely clear about this, you have light coming straight from the emitter to the back, to the detector, let's say, to the screen. But you also have some that are taking a slightly longer path by having to be reflected off of the walls of the slit themselves. Because of that slightly longer path, the phase of the wave that's reaching that same atom at the back, there's one atom at the back, but it's getting input now that is a longer path, and it's getting input that is the straightest path. Because of that, there's the opportunity for those 2 phases, the right-handed tug and the left-handed tug, to occur at the same instant, and you get cancellation in that case. But I again, like, I want to be really, really clear. Like, the value of this model is being able to picture, imagine, visualize, think in terms of materials of what could be producing the phenomenon. We're not actually adding anything to the empirical mathematical space. We're just interpreting it. So when you say, will this improve the empirical mathematical abilities, I'm not so sure. But what I think that it really could do is help young engineers imagine solutions to technological problems that we can't get past. Problems with manipulating gravity, with manipulating light in new and unseen ways. That's really the value of this framework. It's not going to be refining the basic empirical science. Maybe, I don't know, if some brilliant scientist was able to access his imagination and her imagination in a new way, that would be great. But fundamentally, all we're doing is giving form to the ideas. We're not giving new ideas per se at this point.
Well, I think talk about imagination, right? A big thing that the whole double slit experiment has opened up is the many worlds hypothesis. And there's entire movies now about the multiverse and what that could possibly mean. And I enjoy thinking about some of those things. And there comes a point where those, fictions have a tangible impact and a positive effect on my life, just how I think about the actions I take, and that instead of just kind of taking an action as boring world here, I'm now taking an action, and everything I do propels me into another universe now where this new reality is manifested and whatnot. So that's even kind of fun and everything. But yeah, like you said, even more technical things that we can apply with maybe gravity and all of that. In fact, that's where I kind of want to switch over, right? We just talked about like the tiniest things, the double slit experiment with single photons. The nearest star that we know where it is, other than the sun, isn't that like Alpha Centauri or something? Like
I
which
think
one?
it's Proxima Centauri.
Proxima. Do you know how far away it is exactly?
I've looked
We can
at
look
this.
it up. I think it's a few light years away, let's say.
I think it's like 4 light years away.
So then here, how do we see light? Because we see that star, right? How do we see
absolutely.
light from a star that's a couple light years away?
Hey guys, if you are enjoying the content that we are producing here at Material Atomics and you're interested in seeing these ideas come into a more beautiful form, one thing that we've started to do is work with an animator to make more beautiful pictures of these ideas that we're putting out there. And our animator, Peter, does animations for a living. He's been working with us for free up to this point, and we want to start getting him some cash so that he can justify the time. So right now, we're going to be giving him basically enough money to work on this at least an hour a week on the animations. If you want to help us grow that budget, you could come over to our Patreon page and give a couple dollars a month. You'll also get access to all of our podcasts early and all of the fun that comes along with being a patron for the Demystify Sci podcast. But fundamentally, we're going to be putting more and more money towards our animator so that we can get better and better videos out here on Material Atomics. That star, and any star, is a lot of atoms in one place. They're all very hot and they're emitting a lot of radiation. I think it's really important in terms of addressing any astrophysical and cosmological questions to realize that under the model that we're proposing here, light is fundamentally a conversation, and it's a relayed conversation. So anytime that light is traveling across the room, it's making its way across a lot of atoms in the process. And there's a lot of transactions occurring along the way. And so when we point our telescope at the sky, we are looking at light that is not direct from that star, but it's being relayed through our atmosphere, through all of the different gases that might be wandering in the intervening cosmos between us and that star. And so, how can we see that light? Well, there's a lot of light coming off that thing. And there's also interactions along the way that are changing the way that we see it. And they're changing that light. When we talk about light that's coming from 14 billion light years away, it's unimaginable to me that you wouldn't be affecting that light along the way, because there's no way that such a relay process isn't going to drain energy from that light as it travels.
I was going to ask, why would you expect that we would have a hard time seeing the light from stars? Because the question has inherent in it the assumption that it's weird that we can see that light.
No, I was more asking for the mechanistic process, not like how is it possible that, but explain to me what mechanisms need to happen so that I can look up there or point my telescope up there to see it. Like in the traditional model, we say, oh, there's a star and it shoots out these photon packets to us, and then we see them. But now with your approach, I mean, my initial thought is there is some straight wire going all the way to that star, and it's 4 light years long, and that wire, zoom, that's where the photon goes along. And based on what Michael was just saying, I'm not sure if that's the right picture that I have in my mind now.
Turn that wire into something that has sections. And at each section, there's an atom. And each atom that is the endpoint of that section will relay its signal onward to the next atom. And I think that the impetus for the direction that signal will travel is the star in the first place, because light has momentum. And so you can imagine that you have a photon that is traveling in a filament that leaves Proxima Centauri, and it hits the first molecule of gas or whatever that's in the sun's chromosphere. And that atom of gas has a radial architecture. It can transduce the photon in any direction, but it doesn't just, and some of it just scatters, right? Because we know that when you have gas in front of something that is emitting light, you're going to scatter that light. So some fraction of it does scatter. It does not go straight through. That's what makes something opaque. That's what makes it. That's the difference between an optically transparent gas and something that is not optically transparent, is that you get more scattering. And so the light from the thing that is emitting the light doesn't make it as well to your eye on the other side of that cloud. Okay.
And if I might just interject, that the majority of the gas out there is neutral hydrogen, and the way that astronomers treat neutral hydrogen is that it doesn't interact with light, which is preposterous, because what we're saying is, no, it does interact with it, it just relays it on forward.
Exactly. And so you have light you have a photon that is emitted from Proxima Centauri. It hits a gas molecule. That gas molecule has two options. It either scatters it, I guess 3 options: scatters it, absorbs it, or relays it. Scattering is a form of relay, but it is not directional in the same way that allows us to be able to see the light, all of the light that comes from Proxima Centauri, right? Isn't this Euler's paradox or something about the
Olbers? I think it's called Olbers paradox.
Olbers paradox, which is that, okay, so if the entire night sky is filled with stars, why is there a night sky in the first place? We should be able to see all of the light from all of those stars at all distances and all points. And so the night should come and the stars come out, but they're so bright that they basically make it so that there isn't night. And the reason that there is darkness is because not every single photon that is leaving Proxima Centauri makes it to us, but there is a chain of atoms that is 4.2 light years long that actually carries that signal from atom to atom, and that's the momentum of the light as it leaves Proxima Centauri that is what causes it to travel in that straight line. Does that make sense?
It sounds like the original misconception there is that it's just a vacuum between my eye or the detector or whatever it is and the star. And it's obviously we have the atmosphere, and that's kind of something you'll think about. But then you also propose there's not vacuum between the atmosphere and the star. There's a whole lot of other things in the way that ought to be considered when even thinking about that.
100%.
Yeah, and I also have this thing that I think that Shiloh doesn't particularly like because it's a little bit spooky. But I'm like, if you have something that's sufficiently far away that is emitting light, but for some reason it is not connected with the network of atoms that would relay that light towards you, you'd never see it. And so you could technically have a multiverse. I know that I feel like I'm pandering to the audience right now. Shiloh's shaking his head, disappointed in me. But I'm like, look,
I just think we're getting into the weeds. Like, we should stick with like interpreting what we can see.
I mean, isn't that though the idea behind the observable universe?
That's exactly right. That's what I'm trying to
Yeah,
say.
actually, one thing that people don't realize is when astronomers say universe, they literally mean what we can see. That's it.
Mm.
So if you strictly hold them to their word when they're talking about the edge of the universe, what they really mean is that's what we can see. That's the edge of what we can see, which I think is a very charitable way of interpreting a lot of this discussion about, you know, the time period of the first atoms. What they mean is what was happening when those atoms that are the furthest away we can see, what they were doing, which is, you know, a lot less spooky. But that's really, if you hold them to their definition, that's what they mean.
I mean, that's really, we can get into Big Bang stuff and whatnot. And I don't really want to go down that rabbit hole, to be honest, because of course it is or obviously connected somehow that, you know, our ways of looking at things, if we don't model them properly or how we model them, will determine our entire cosmology, basically, right? If we model things with cause and effect, then we always have to ask, well, what caused the cause that did the effect? And you can rewind it and whatnot. And that's, I guess, how we arrive at some of these theories and models and myths that currently exist. And what I find more interesting, though, is general relativity proposes that space-time is like a thing that's influenced by energy and mass or matter. And the way I've started to picture that is as a node network like thing. And I've also seen some great visualizations online where you have like, okay, what does gravity look like? And they make this cube-like structure, this grid, kind of like you see when you have these polygon animations, and they don't have textures, but they just have those lines between them.
Yeah, they're like filamentary lines.
Exactly, right? And so then the gravity is kind of like all those lines point toward the massive object. And so there's no more that space-time as the background of the universe where things happen. But in your model, you're kind of like, I guess, unifying them. And you're saying like, hey, the what you call previously structured ether, you know, I know the word ether kind of has this connotation, but space-time and the atoms, they are connected, and this is how they're not. Space-time is not just this geometrical construct, but it's an actual part of our universe. And to me, that is a bit of a paradigm shift, I guess, but also it makes perfect sense.
You have no idea how happy it makes me to see those videos of this is space-time visualized and it's a filamentary model, because it makes everything that we're doing that much simpler, because that's exactly it, actually. And moving away from this idea of space-time as being this fabric that has just depressions inside of it and things follow curved paths because the fabric is curved, makes it's much farther away from the way that we're thinking about it, but this filamentary model that people are starting to build and put up on YouTube is much closer. And so to me, it says that we're on the right track, because this is the zeitgeist of how people are starting to think about it, because they're like, oh, well, it probably can't be a planar flat sheet the way that it's always drawn in visualizations. Right? It has to be in 3 dimensions. And if it's in 3 dimensions, then it has to have an architecture. And if it has an architecture, then how can we model it inside of Blender or inside of an animation program? And it turns out the easiest way to model what it might look like is to use filaments.
Yeah, I might add to that I have kept a running blog of every single time that I see someone in pop science drawing filamentarily connected atoms, and there's a lot of them. Every time there's a pop sci article about entanglement, they draw filaments between the atoms. You'll often see it with things talking about subatomic structures. You see it with the universe, the cosmos in general, when people are talking about these the wide scale structure of the universe. It's the people are kind of ready for this filamentary model. It seems like they're already using it without actually treating it as a bona fide possibility.
And I think what you're really doing here is you are examining the exact structure of the filaments rather than to be like, hey, they're just lines between points. You've actually gone into the details of, well, what if it's like a helix shaped thing with these types of properties, and so it acts like a spring, and there's a lot of detail that can be developed to deepen our understanding of the universe and how things work. And that's what's so fascinating to me as well.
Yeah, I mean, we've kind of walked back on this helical stuff a bit because we've changed fundamentally how we think about light as being this back and forth tug, which of course, if you move the axis of the atom, you get all sorts of polarizations out of it. You can get you can get a helical pressure that's being applied, but the simplest case, it's really just a back and forth pressure. You have this transverse wave in the filament. And one thing that we can do, and we've started to assimilate, is there's been a number of mathematicians who have been like, hey, if the ether was a thing, what are its material properties? There's a great essay, an article published, I don't remember what journal, by a gentleman at Princeton who went through a number of different modeling regimes to examine the stiffness of that structure. And so we can learn about the material which is conveying this force of light, this force of gravity. We can learn about the stiffness and how it's actually capable. And what we learn is that it's unbelievably stiff, actually. And, this feeds into our understanding of why is light so fast? How can this material disturbance travel at such a high speed? Well, because that guitar string is under unimaginable tension. And we know that that's what happens when you put things under tension. That when something is really stiff, that sound waves in it move really fast. And this isn't exactly like a sound wave. It's a transverse wave, right? It's this back and forth motion. But
like a guitar string.
Like a guitar string. It's just like a guitar string. But those oscillations are informed by the stiffness, and they make sense in the context of everything we know about the tensions that it should be able to hold. And so these all conspire to give us a picture of exactly what you're saying, of what that structured ether looks like, what its material properties are, what it is, what it could be, what makes the most sense. So yeah, we're saying, hey, spacetime's a great analogy and everything, but there's actually something that doesn't look too different, which could possibly accomplish this incredible feat, a real material structure, which could accomplish this feat. Let's give it a try.
So I have a bunch more questions here that I was going to go down, but based on how you just talked about that, I just sense explosive potential personally. Can you explain how fission works, nuclear fission, which I guess maybe people are kind of reminded of it too with the Oppenheimer movie that came out just now. How does it work in common understanding? And then how does it tie into your model? How can we think of nuclear fission?
Well, we're working on a book right now, right? So we're really obsessed. We decided to narrow it down to just light and gravity. And we're definitely going to do another book about electromagnetism in general. And I think the one after that's going to be about nuclear processes. So it's like very far at the back burner for us. But what I can definitely offer you right now is that fission, the central actor in fission is the neutron. And what we've done in our understanding of the neutron, because what happens is you have these chain reactions where neutrons are ejected, they impact other atoms, and you get this chain reaction where the nucleus swells up with these neutrons. This is schematicized. This is how it's described. It bursts, the atom splits, more neutrons are released, you get this chain reaction. So what the hell is a neutron is the biggest question that was on our plate for a long time. Because the neutron's a really interesting little character. And what we have arrived at is essentially an idea that can be traced back to this English chemist named Prout. And Prout had this observation that all of the atoms in their size and their mass seem to be essentially multiples, let's say scalar multiples of a hydrogen. In other words, all of the atoms seem to be built out of hydrogens. Okay, so that's one piece of the puzzle. Hold that on one side of your brain for a second. The other side that's really interesting is that neutrons don't last very long in the environment. If you have a neutron and it's just flying around in the room, you got about 15 minutes before that thing falls apart. Now, what's really interesting is when it falls apart, what it falls apart into. Because what it falls apart into are essentially the components of a hydrogen with a little bit of extra juice. There's some extra energy, which they call a neutrino. And so what we have come to model in our world here is that what's actually happening is that a blob of material is popping off of that atom when the neutron is produced. That blob of material has all of the material to form a hydrogen atom, but it's not quite there. It's like a little tadpole that isn't quite a frog yet. It doesn't have the ability to electrically behave itself. It can't interact in the same way as a fully flushed out surface of a hydrogen. And eventually what happens is that it stabilizes into a fully fledged electrically active actor, and we would call it a hydrogen. But it's the same thing as a neutron. It's just now electrically active. And so all of our understanding about these nuclear processes come down to the production of new atoms blebbing off of the original atom in the form of neutrons, which eventually stabilize as hydrogens.
And at the end of the day, the nuclear components have to be a product of the motion of the shell. Because the way that we've designed our atom, the way that we've interpreted the mathematics, is that the electron shell, which we basically call the electron the outer surface of the atom. And most of the diagrams that we've done have just been with hydrogen because it's such a simple shape that you can work with it and you can think about the proof of concept without having to get into the P, D, F orbitals, which are crazy shaped, and then you have multiple layers of them and you have this very, very difficult geometric consideration. So we stick with just the hydrogen, which is a 1s orbital, which is always drawn in these diagrams as just being a sphere, right? It's just this kind of circular cloud of probability of where the electron is. And then you have that at the center of a hydrogen, you have some kind of positively charged molecule. And they're not related.
Not molecule.
Particle, sorry. They're not really related to one another. They just happen to be opposite charges. And then you have this other thing, which is like, okay, well, if they're opposite charges, then how is it that the electron doesn't just crash into the nucleus and remains in orbit and just floats around? And so in order to deal with that, we're like, okay, so the electron is the shell of the atom. And we know that it has SU2 symmetry, which is that it has to have two involutions in order two rotations to come back around to the place where it started. And if you have if you have two different motions that are happening at once, then you can get that kind of symmetry, which is that it's rotating around its axis, which is one rotation, but it's also involuting inwards, and that involution takes two rotations to get back to the starting point. So it's basically this torus that's folding in on itself that is then also rotating in space along its polar axis.
And if you're having trouble visualizing this, we have a nice animation of it up on the channel. You can check that out.
And I will make a timestamp so that we add the animation right here. So before I lose my direction here, I think that it's really important to think about the positively charged nucleus in context of the negatively charged shell, and how, if you have this involuting motion, the nucleus is going to be oppositely charged from the shell inherently due to the geometry. Because as the shell travels up, the interior has to travel down. And if the motion of that electron is what gives you its charge, the motion at the center will always be opposite than the motion on the outside. And so when we talk about, Shiloh's saying that you have this neutron that's shot off and it's not quite a charged hydrogen because it's not interacting electrically appropriately, what that must mean is that there's a fracture in the atom that is releasing the neutron, and that fracture is transmitted into the network as motion, but that motion isn't coordinated yet. It doesn't have the symmetry that it needs in order to produce this electrically active hydrogen. And so the fission process can only be told through the story of understanding what exactly is the geometry of the nucleus, and how can you take a nucleus and split these nodes of motion away from each other.
Yeah, like just to be clear, we're not saying there's a bunch of little balls or something at the center of this atom. We're not saying there's a bunch of separate electrons on the atom either. We're saying that the same material comprises the nucleus, that comprises the shell. They're just different structures. At the center is this constriction, which is from this vortex of involution, which we can infer from the charge behaviors of those. But we're saying that when you pop off a chunk of the atom as a neutron, it just isn't formed into the shape of an atom yet. It isn't capable of interacting with other atoms as an atom yet. And so it has this neutral behavior. That's strictly due to its structural incompleteness.
Like, I think I have a feeling that a neutron is probably really chaotic.
Yeah.
Like, I think that when you, because electrical interaction in our model is very harmonic, very concerted motion, right? You have chains of atoms that are geared into one another. They're all spinning together, and their concerted motion is what is producing electricity. And so if you don't have a concerted motion, then you can't interact electrically. And so to me, it makes the most amount of sense that the neutron is still this kind of chaotic mixture of fiber, which is what we think that the atom is made out of, right? The fiber orients into the shell and into the filaments. And so it's the constituent of the atom itself. It's the smallest piece that's inside of our model.
And if you think about it, it's like, where does that extra energy, what is the neutrino? Well, because when a neutron disintegrates, we're saying it disintegrates into a hydrogen. Well, mainstream fundamental physicists would say, well, you get an electron and a proton, and you get this extra stuff too. And we're like, hey, it makes sense that if the atom is going to form from a neutron, that it would be an energetically favorable process. It should release energy. It should be easier for the atom to be shaped in this toroid involution fashion than not. And so when this material is ripped off or kicked off or spallated off, however you want to think about it, when it blebs off of the original atom as a neutron, it's not in an energetically stable fashion. It's not happy like that. It wants to configure itself as an atom, and we know that because it gives off some energy when it finally turns into that hydrogen at the end of the day. And that's the form of the neutrino, which is essentially a wave of radiation that's dissipated into the network around it.
The whole idea of energetic favorability, assuming that how we measure energy is usually through photons. There's other ways too. But the energy of the universe, if I think of your model, seems to be these fibers. Like the amount of fiber stuff we have is the amount of finite energy we have in the universe.
I guess all I mean by energy is like it's easier. It's easier for something to happen. When I say something's energetically favorable, I'm like, it's easier for a ball to roll downhill than roll uphill. It's just easier. It's energetically favorable.
I also want to add that I don't think that it's the fiber itself that is the energy. I think that it is the motion of the fiber and the way that it is organized.
Yeah.
So it's like, think about it in the sense of just wind currents versus a hurricane. They're kind of the same thing. It's just air moving, but you get into this place where the air moves in just the right way, and you have just the right feedback mechanism that accelerates the way that it grows into a storm, and you get a hurricane. Under slightly different conditions, you wouldn't get the hurricane, but the idea is that the hurricane occurs because it's energetically favorable, and so if you come down to the atomic level, everything has to be in absolutely insane amounts of motion. Like the cesium atom, which is at the heart of an atomic clock, vibrates at 9 billion cycles a second. Right? So everything that is happening with a tremendous amount of motion. And that motion is most favorable when it's harmonic and pulses with the network as opposed to fighting against the network. And so all of that motion of the fiber organized into atoms, organized into filaments, is the energy. It's not the fibers just lying on the floor.
Yeah, you have a hard time defining energy in any other way than something doing something, right? It is the doing. It is an activity.
The proverbial you.
Yeah, one has a hard time defining energy. It has to be some material in motion. And of course, you can have potential energy, which is like it has the potential to go into motion. Fair. But ultimately, go ahead.
Speaking of energy, and we just talked about kind of fission, and I think there is some room for reinterpreting what we have empirically tested and all of that. When it comes to fusion, we've had some headlines recently that maybe they made progress. They've been trying it for a long time, it seems. In your opinion, what is the misunderstanding, the misconception about fusion? What's the bottleneck there that we can identify using your model?
I mean, this is a huge beloved topic for us. It's more of an astrophysical model, but I do think the Material Atomics project has something to say. So I think that the problem with fusion progress fundamentally comes down to the misunderstanding the material nature of stars. This is something we've dealt with a lot on the podcast. But the reason we think that comes down to how light is produced. Because what's very strange is that if you look at a star, it gives you this beautiful black body spectrum. Now, what the hell is that? Well, when you heat up a piece of material, it gives off light. This is called black body light. And all it essentially means is you get a rainbow of all of the different types of light. And, that's been known for a very long time. And, we have an explanation for that because if you have a gas, it really only can give off discrete frequencies, and that's been known for a long time. Well, why is it that a gas can only give off a few frequencies when a material body can give off a lot? Or almost an infinite number of frequencies at varying power? Well, the answer is that when you have this aggregation of atoms that are connected, you have the ability for your antenna, right? Remember, this is an antenna model of light. The dimensions of the antenna tune the frequency of the output of that light.
And if I can add something to that, what you're seeing when you look at a gas molecule and you look at line spectra, what you're seeing is you're seeing the modes of vibration that are available to that antenna.
And when you start sticking them together, you multiply the modes that are available.
Which is the difference, I'm sorry to interrupt you again, but it's the difference between gas phase matter and condensed matter. You hear people talking about condensed matter, and you hear people talking about black body radiation as being the product of condensed matter. And this is what Shiloh's trying to get at, which is he's like, the antenna of the condensed matter, which is multiple molecules networked together with conduction bands as part of the substance, is a different physical space. It has a different ability to emit than just the atom alone, because the atom alone that's just floating in space has a few really simple modes of vibration available to it, and those simple modes of vibration, the bending and the squeezing and you can look up a diagram of these various atomic vibrations. Those are limited in a way that this black body radiation is not.
Yeah, you gotta imagine that every time you articulate, you add another piece onto your ball and stick model. Every time you start gluing atoms together, you get new modes of vibration. There's new lengths available, which means that antenna can change dimensions, which means that you have more frequencies of light that can be emitted. And so, just to bring this back around, all of this that we're saying, it hopefully makes sense, but shockingly, this is not how stars are thought of. And this is really, really problematic because stars are treated as balls of gaseous plasma right now.
And there is a mathematical proof that people use to be able to say that the reason that you get black body radiation off of this ball of gas is because of something called Compton scattering, where the photons just bounce around inside of the sun for millions of years until they come out the other side, giving you this perfectly neat black body. And so what they're saying is basically the same thing that we're saying here, which is that the material properties produce the black body spectrum. They just have an extra epicycle onto it in order to allow a gas to do that, because on Earth, a gas could never give you a black body spectrum.
Yeah, I think it's worth pointing out for people who aren't well steeped in this topic that no one's ever produced the black body signature, this beautiful, characteristic light curve that you get from heating any material body anywhere on Earth. You can do it in a laboratory, you can do it at home in your garage. You heat a body, you get this black body spectrum. And you can't take a gas and do that. No one's ever even come close to producing a black body spectrum with a plasma or a gas in a laboratory on Earth. The only example that they'll use to say, they'll say, all physicists out there, all of them I've ever talked to will say, no. Gases can give black bodies, and you say where? And they say stars. But you see how that's a very circular argument, because if you can't actually do it, then you have to come back to the fact that, hey, I think that the stars are not actually gaseous plasma. I think that there's some sort of lattice, even if it's a transient lattice that's being arranged, much like lattices can appear in water as well. It's quite interesting. Water is treated as a fluid, right? Okay, it's always chaotic. No. Actually, water has transient lattices. You know, if water freezes, it has a very obvious lattice to it. But water under pressure and at surfaces forms a lattice. And so something similar must be happening in the star, where the hydrogen exists in a form that is transiently metallic, in that it can form some sort of transient lattice with one another. And you have something that's more liquid-like, actually, than gaseous.
Bring this home to fusion. Because the question is
fusion bottleneck. So let's get back to fusion. So if your entire approach to fusion is we're going to bring the power of stars to Earth, and you fundamentally believe that the stars are powered as gaseous plasma, which is operating under this enormous pressure of gravitation, then you're going to miss out on this wonderful form of fusion called lattice-confined fusion, where when you do have a lattice, you can trap elements in between those sheets of the lattice, and you don't need extraordinary temperatures and pressures to produce lattice-confined fusion. And there's a group at NASA that's been picking away at this, and it shows up in the news every once in a while. And I wonder if they aren't working a lot harder on it than they're willing to lead on, because lattice-confined fusion is extremely promising in that it can take place at ambient temperatures, and that it doesn't require these enormous pressures like you would expect at the heart of the sun. So if fundamentally we have misconceived of the material nature of stars, which by all accounts really looks like we have, based on every test you can do in a laboratory here on Earth, it doesn't seem like you get a black body spectrum out of a gas or a plasma.
And so the fusion bottleneck, in order to answer the question, is that the mode of experimental design starts with a misconception of what a sun is. And so you'll never be able to get to fusion if you're starting with an incorrect model of the only place in the universe where you think that it's happening. Your model has to be reflective of reality. Otherwise, you're just kind of trying stuff that maybe you'll be able to get some tantalizing clues in that direction and kind of keep putting money into it and keep working on it, but it's not going to be a blockbuster, because what you're doing is you're trying to scale an energetic mountain that isn't how nature does it.
Yes.
So would you say that your material model of the atom helps us better understand how stars work, or is that a bit of a stretch, or how do you know what you know, given that you came up with the material atom?
Yeah, I think we maybe kind of glossed over that, but I think that that's what we really can bring to the table, is that right now, the astronomers and the astrophysical community in general is willing to entertain the idea that a gaseous plasma, under some extreme circumstances, can produce a black body spectrum. And, it's a very hard argument to counter, because they're saying, no, stars are the exception. They can do it because they have more pressure and temperature than we're capable of producing on the lab. Therefore, we'll never be able to do it in the lab. Leave us alone. It's not a laboratory thing. And that's a very hard argument to counter unless you say, actually, the reason that a gaseous plasma can't do it is because of the way that light is produced from an atom fundamentally. The reason that gases give line spectra is because of their vibratory modes with respect to how light is generated. The reason that a condensed matter object gives you a black body spectrum is because of the material nature of the way that antenna is set up and the way that light is fundamentally an antenna process. So we're saying that the production of a black body spectrum from a gas not only hasn't been observed on Earth, but it's not possible. You can't do that. There's a reason why black bodies are only produced by objects that are condensed matter. And it has to do with their atomic structure themselves. It has to do with all of those extra vibratory modes in that nodal network that are set up that are not available to the gaseous atom. So it's almost like we're not splitting hairs about the empiricism anymore. We're not like, well, just because you can't produce it means that the star is condensed matter. No. We're saying it's not possible for the star to be anything other than condensed matter because it wouldn't make sense to generate a continuous spectrum of radiation from anything other than a piece of condensed matter.
Seems like a good segue here. I don't know if you think it's good too, or if it's just my ADHD or whatever. But what is mass and what is gravity, and how do you explain that with your model maybe differently? Because from what I understand, you make a close link between light and gravity, which I mean we kind of know that also from general relativity with the whole gravitational lensing, right? So that's one of the aspects where we see that gravity does indeed impact light. Well, what do you say? What is mass, and how do you model gravity?
I think that is a good segue, first of all. So I think that
Thanks.
that's... I mean, I think I'll start with how we model gravity, and then hopefully I can get to the place where I can give a concise explanation of mass. But gravity has to be the product of the filamentary network, which is to say that the filaments that go between atoms are stiff objects, but we know that atoms must be able to also transect them, right? Because as you move through a room, you can move through the room. There's not some spider web that you're constantly, that's not clinging to you that you're having to brush away. And
unless you climb a hill, then you'll really feel the spider web.
Unless you go outside. But if you think about it, there is kind of a pull on you, right? Because first of all, gravity, when you're sitting in a chair and you want to stand up, there is an extra amount of work that you have to do in order to do that. And then if you're standing still and you're not changing your gravitational potential whatsoever, you still have an inertial resistance to beginning that motion. Okay, so we have two things here. We have gravity and we have inertia. And they both emerge from this filamentary connection between objects, where if you have filaments that are connected between all of the atoms in the room, then breaking a filamentary connection and reforming one as you move through the room is going to take some amount of work. And the work that it takes is inertia. The amount of effort that you have to make to go from standing still to moving, the amount of displacement that my arm makes as it moves through the space in front of me is the result of needing to break these connections when it's here and form new ones when it's here. So if we have that inertia is a product of the network, then gravity is also a product of the network, because when you have many, many atoms in one place, they're going to send out a greater density of these filaments to the other atoms that are around them. And if it takes effort to break a filamentary connection, then it's going to take more effort to break more filamentary connections. And so when you're near a very, very large body, you have a lot of these filamentary connections that you have to work with and you have to overcome in order to be able to move against the tension that wants to just drag you back down to this massive body. And it's interesting too that gravity falls off with the inverse square of distance, which tells us that if you have a radial surface, the force is going to fall off with the amount of connections in a given cross-sectional area. And so when you're very, very close, you have an area that has, let's say, 4 filaments moving through it. And as you double your distance, you're going to cut down by 4 the number of filaments that are in that space. And so now you just have 1 filament that's pulling on you. And so you go from having a lot of gravitational interaction.
It's a square, so I guess you'd be at 2.
Oh no, you're doubling the distance.
Oh,
So it's a 4.
2 squares.
2 squares, 4.
4 divided by 4, 1, yeah.
I think part of the reason we all kind of like this material thing is because we're not that good at math, at least.
I'm glad that I got that right, because as I was saying it, I was like, so he's going to get me on this. But no. So basically, you have a radial architecture of filaments that as you move away from this agglomeration of bodies, then all of a sudden you are interacting with fewer of them, and your inertial context changes as well as your gravitational context. Now,
as I was listening to you, by the way, like I so experienced the sensation of this makes sense. Like it just there's
so
no friction
good.
based on how I understand things, and it's really refreshing, especially when it comes to gravity and mass, and which is related to energy. It can be so difficult to understand that, but this whole spiderweb thing, like it makes sense. Like I don't know what else to say. It just makes sense the way you explained that.
And that's why we're here, right? We were in that position, man. Like I was so obsessed with this when I was a little kid even. I remember seriously like crawling around in the basement of our library trying to read physics books. Like, how does all this stuff work? And it was just so abstract and so I devoured these physics books and they just didn't have answers. And like I literally like was so excited to go to Columbia and do my PhD because I knew there was people there that I could talk to, and I was like, these guys are gonna have the answers. They're gonna be able to explain it to me in a way that makes sense. And meeting those people and having those conversations and sitting in their office and just being like, holy shit, like nobody knows how this works. Is really what's driven us to this place that we're at right now. Where we're like, no, like we're gonna make sense of this by the time we die, no matter what. Like there is an answer out there, and nobody seems to be working on it. And let's do it.
Do you want to put the bow on mass?
Yeah, sure. So mass is an interesting concept. I mean, mass obviously scales this connectivity. So an atom that has more mass is going to have more connectivity to its surroundings, and
which might just be a surface area thing.
It might be. I think that's probably the easiest way to look at it is in terms of surface area, because especially if you think about that neutrino, right? That little blob of material that's popping off of an atom during fission. It's like, well, presumably that is constructed of the surface of the atom it came off of, right? We don't think that there's a bunch of little things in the center of the atom and it's the neutrons hiding out in there until it comes out. We're saying, no, a little bleb of material pops off the surface of the atom. Well, by blebbing off the atom, it already contains all the connections that it needed to all of its surroundings right there, because it's going to take those connections from the atom that it came from. And so when an atom gets a neutrino, sorry, did I say neutrino? A neutron. If I said neutrino earlier, I'm sorry, I meant neutron.
I'm sorry, I was visualizing so hard that I didn't.
So when this neutron is the bleb of material that comes off during fission. When an atom absorbs a neutron, when it gets a new chunk of material, right, an atom's worth, a hydrogen's worth of material, it brings with it all those extra connections too. And so as you build atoms up out of neutrons, out of essentially inactive hydrogens, you're adding all of those connections that thing had before to its surface. And so you're scaling up the connectivity of that atom to its network, the greater and greater in mass that it grows. And so mass is fundamentally just a scalar that tells us what number of equivalent hydrogens worth of connectivity you're adding to that new atom as you go up. And so something that's really heavy has a lot more connections. Something that's light doesn't have that many connections. That might be because there's less atoms in that jar, but might also be because the atoms that are in it are essentially more massive. They have more connectivity. And it might be a surface area issue as well, where they're able to host more connections because their surface is larger. I'm not sure it's more convoluted. It has more folds in it, right? Surface area has a lot to do with folding and nooks and crannies available for connectivity. But in any case, it appears to have absorbed all of the connections of that neutron that it took in when it grew. And that's what we think is happening.
It makes me think of the question of quantum gravity and microgravity, and what is the smallest unit of gravity, and could you quantize it? And it sounds like you might be on a path there to maybe not answer these questions, because that's what I've noticed a couple of times I ask you questions. I feel like I'm asking the wrong questions because you give me very different answers than I would expect. But yeah, can maybe not answer the questions, but shine light on the question and help us find better questions to ask to make progress on these things.
Well, a lot of times the framing is a little bit misconceived, right? Because, the neutron's treated as a particle that hangs out inside of the nucleus. Well, we don't think there's any reason to believe that's the case. We think that it's a schematic that works really nicely for engineering, but that in reality, there's a physical process, a material process that's happening. And so if your framework is a little bit off, then answering questions about this completely hypothetical room inside of the center of the atom where all this stuff is taking place is not the right question to be asking. We really need to start with what's observed and how can we give that material form in order to imagine what's actually happening. That's congruent with all of these experiments. And so that's really what we're trying to do. I mean, you talked about quantum gravity. I mean, again, I think this is a case where the framing is a little bit misappropriate, because the explanation for mass that we just got done conveying doesn't have any context outside of atoms, right? You don't have mass below the scale of an atom because mass is fundamentally a gravitational process. But what you can do, and what the atomic physicists have done, is they'll say the equivalent force of mass. So they'll assign these subatomic particles masses, but what they really mean is the equivalent deflection force necessary to produce what we would call mass at the atomic level. And so this word mass gets a little crazy, and people start diving in the weeds trying to understand how the gravity works below the level of the atom, when gravity is fundamentally an atomic process. It makes no sense below the level of the atom. You can talk about what other processes are causing those forceful interactions, but gravity and mass are not really the appropriate word to be using for those phenomena.
But when we talk about quantum gravity, though, I just wanted to double check this, and so I'm looking at the Wikipedia page for it, and it is that they're trying to describe gravity according to the principles of quantum mechanics. And I think that that's more or less what we've done, which is that we've said that, look, the foundational principle of this entire model is that you have this radial distribution function of the atom that says that all atoms have surfaces that extend to infinity. They're rarefied, but they do go on for pretty much as long as you want. And we know that the fabric of space-time has a stiffness, and we know that the fabric of space-time is very, very stiff. And so if you combine an infinite atom to a stiff fabric of space-time, then you almost have there's no other possibility in my mind that allows you to exert force, right? Because we talk often about the idea of particle models and the idea of there being a graviton and the graviton being able to pull on stuff. And it's very, very hard to imagine how a bowling ball of particulate matter would be able to pull on something. You'd have to then have something else, like we had a friend who gave us this chain of little circular magnets, and you can make a string out of these circular magnets, and then that string actually does pull. But then what you've done is, I can see puzzlement on your face.
No, I'm picturing right now a string with magnets lined up, and it seems like a fun idea to model something.
Well, they're basically just little magnetized spheres. They're like neodymium spheres, right? And so you can make a string out of them, and then you can attach like a paper clip at the end of it, and then you can pull the string, and it's like, oh look, you do actually have pull that's out of little round particles. But in order to achieve that pull from these little round particles, you have to introduce a different force, which is magnetism.
Right.
And so your model becomes much more complicated than it would be to say that, like, hey, they're not little round bowling balls, but it's actually an object that is interconnected between the atoms because it is the extension of the atoms themselves.
Yeah, like how do we accomplish pole here on Earth? We use cables, right? That's how you do it. And so it makes a lot of sense, at least in terms of modeling this thing, that we should be looking for some cable-like structure as well. And it just so happens that solves every other problem with light at the same time. And so it's kind of like, well, it could be wrong, but it's certainly a pretty cool coincidence.
To me also, that's exactly what the spacetime tensor describes, if I understand the stuff right. But there is some type of tension between things that kind of models everything, like Einstein was saying. What confuses me in visualizing all of it, though, a little bit with your model, is every time I see an animation of it, you make it spin. And so now suddenly all this cool network that I can now imagine where you talked about the spider web, now suddenly it's no longer static spider webs, but it's spider webs that spin around themselves, and so there would be constant.
Yeah, we've ditched that completely for the exact reason. Yeah, we had the same unease about that. And so, yeah, we've been forced to realize that those connections must remain at least tensilely static between any two atoms that are connected to. So in terms of electricity and magnetism, there's a different process that's happening at the shell. That surface is definitely spinning and is responsible for electricity and magnetism, but those connections remain in place. They have to. So that's, yeah, we have a couple old animations of electricity and magnetism where we do have spinning filaments right now on the channel. And we're really trying to replace. We have a new animator working with us, Peter. Shout out! And so we're reanimating electricity and magnetism without the spinning filaments now.
It's a little bit embarrassing to be working on this in public because as we put stuff out, we will realize that things don't make sense, or people will point out to us that things don't make sense, or people like you will ask a question that is obviously has an absurd answer, and then we go down the rabbit hole of, oh my God, well, what does it actually mean? And so we have a ton of stuff that's out there that isn't quite right. But I think that the spirit of the project has to incorporate that into it, because we're not coming at this from the perspective of, this is the word of God, we have figured this out, you have to believe what we have written here because this is the final truth. We're kind of coming at it from the perspective of, hey, I think that there are fundamental principles that are in play here. It's a very, very complex and complicated field to wade into, and we're going to make a lot of mistakes along the way. And as long as everybody involved is a good faith actor that wants to progressively refine the model, then we're going to get somewhere good, because we don't own the model. This is not a piece of intellectual property that we're just striving to control and own. We want to figure out how nature works. And in order to do that, we're going to have to probably try on some stupid ideas before we get to the end of it. And it just seems like far more fun to do that out in view of people than it is to frantically work in some closet somewhere, terrified that we'll misspeak and sitting on it until we're about to die and then releasing the theory all at once.
Yeah, I think I will probably pull those two videos down because they're confusing people. But we're gonna, once we have the new animations up, I think I'll make a playlist that says older versions of this model, because I want people to see how this is done in real time too, and see how we've gone through iterations along the way and how they didn't work out. And maybe we'll make some videos at some point talking about why we changed our mind about these things. I mean, with the spinning filaments, this really occurred to me recently that I realized, like, hey, we can't have spinning filaments because when I run a current through a wire and I generate a magnetic field, I don't have any optical artifacts. It's not difficult for me to see it. Nothing changes. And so that idea of spinning filaments being important in magnetism just wasn't tenable. And we've had to readjust how we're thinking about that. And so it's been ultimately productive, but yeah, I can see how that's confusing, because that was a model that we were operating under for most of the time we've had this channel. So yeah, we'll probably pull that. We're going to put a new one up soon that will clarify it in a different way. But
really, there's a pressing question here for me to better understand the whole model too. And I understand that maybe what you answer, it's just kind of your your current best guess, and that's fine. But what is the difference between a photon, an electron, and the filament as you describe it?
Okay. So the electron is the shell of the atom. It is fiber that is organized into a surface.
And it's in motion. The electron has motion inherent in it.
Which we talk about all the time, where everyone has this thing of like, man, atoms are so weird. They're mostly empty space, but they're so solid. How is that? And it's like, okay, well, if you have a surface that's in motion, it creates a solid object. Like, think of a propeller. The propeller is mostly empty space. You spin it fast enough, you get a surface that, let me tell you, is going to be really freaking hard. Okay.
Indiana Jones.
What's that?
Did you ever see that Indiana Jones movie where like the guy Indiana Jones pushes some Nazi into a propeller?
I don't remember that, but yes,
It's
yes,
like-
exactly. Like, we all know viscerally that if you have something that's mostly empty space moving really, really quickly, you're going to get something solid out of it. Okay. And so when we talk about the electron, it's the surface of the atom. It's the fiber that's organized into this moving, involuting body. The filament has to be a different phase of the fiber, which is I think personally that it gets extruded from the body of the atom. Like, if the electron is this amorphous sea of fiber that's spinning, the filament is an extrusion of that fiber into a long chain. And we've played previously with the idea of what that could actually look like. What shape is necessary for the fiber to be able to both pull and be pulled on in order to create this chain that can bend and carry tension and pull on other stuff. And then, so that is not yet completely clear to us in terms of the specific shape, but we know that there has to be a different phase, basically, of the fiber. So there's one phase, which is the surface of the atom. There's another phase that is the filament. And then light is motion that is transduced from the surface of the atom into the filament with forward momentum.
Well, when you say phase, can you clarify what you mean by that word, phase?
Like a solid, liquid, or gas. Like, basically the phase of, like, if you take water, gaseous water is characterized by having these very transient connections where it's just molecules floating around. Liquid water, you have hydrogen bonding starts to take over, and it gets these lattice shapes that Shiloh was talking about. It gets these stronger connections in between it, and then you go into a solid phase, and all of a sudden the connections are locked much more tightly together. And so condensation of, and if the surface of the atom is kind of this amorphous fluid of fiber, when it's given shape inside the filament, it has different material properties than it would on the surface of the atom.
Yeah, all of the filaments and the shell are both constructed out of the same fiber. The nucleus, for that matter, as well. It really just has to do with what is the structure of that element. The structure of the filament is different than the structure of the shell, and the structure of the shell gives rise to electricity and magnetism. The structure of the filament gives rise to light and gravity. And so they're different parts of the same puzzle that we have to look at. And for a very long time, I was really hoping that we could treat them all the same, but we can't. It doesn't make sense. So we do have to look at filamentary processes differently. The material properties of the filaments are going to be different than the material properties of the shell. And those are both informed by their respective phenomena that they house, right? We can learn a lot about the shell from electricity and magnetism, and we can learn a lot about the filaments from light and gravity. And we can tie them together with the radial distribution function and the electron wave function and all these things. We know that we're fundamentally talking about the same stuff, but there are two different activities in that stuff and different structures formed out of that. Sort of like how you have an arm and you have a head. They do different things, but, you know, they're all still part of you.
Now, in the standard model, as I have studied it a little bit, like I say study as if I study like kind of, done my own research. They have.
I hear you're not supposed to do that, Oliver.
They have bosons, and the other one is, I think, was
Fermions.
Yeah.
Mhm.
And so bosons can be stacked somehow, and that's what photons are in their model, right? And that's where I think, if I understand correctly, you can increase like the intensity of light, basically, or the amplitude of a photon by stacking them. And maybe, if I understand correctly, with electrons, that's not possible. And that's where we get these electron shells and the whole spin thing. And because they can't somehow occupy the same space at the same time. How should I imagine that? If first of all, maybe I'm not understanding something here, so if you can correct me, please do. But how would you model this whole phenomenon with your process?
I mean, I think it's really important to understand what these guys are doing. And what they're doing is they're trying to assemble something very similar to a periodic table. They're looking at different properties and trying to group them into categories. And when we talk about bosons and fermions, they're fundamentally distinguished by their spin property, right? So, a very simple spin can give you a symmetry of rotation that makes sense very easily, right? Like you take a basketball, you spin it around once, you get back to the same point. Spin 1/2 particles, right? These events that occur that are spin 1/2 are different because they have this really weird symmetry where you spin them around and you don't get back to the same place. And so what they've done by dividing things up into these different symmetry groups is they've come away with a way of handling the universe that can be viewed in terms of interactions that have one kind of spin versus another kind of spin. And that's really all that they're separating here. And then they're attributing different groups of properties to each one of these interactions.
Well, I think that what Oliver was asking about was this idea that, hold on one second, I just saw this, which is that so I'm looking at Hyperphysics Concepts. I don't know if you know that website. It's basically this like really old HTML website of a guy who's just, I think he was just really into physics. And so he has all these, he calls them hyper cards because they're basically like little index cards that are all cross-referenced with each other. And he takes physics concepts and he breaks them down in simple ways for you to be able to understand. And he's a really good resource because each one of the cards contains a very small amount of information. And it almost always has some kind of picture that's associated with it. And so it's like a Wikipedia that is specifically for physics. But he says, just like you said, that two fermions take up space while bosons can pile on top of one another. And I think that that's the thing that you were trying to get onto, which is what does it mean to pile them on top of one another? And I don't have a good answer to that yet. And I could probably come up with something right now if I was to just read a little bit about it, because it's basically saying that like the Pauli exclusion principle is an illustration of fermion behavior, which is that you can't have the Pauli exclusion principle is that you can't have two electrons that are moving in the same way in the same orbital. So if you have one electron that's spin up and you add another electron to that orbital, it has to be a spin down. And so you can't take two objects that have the exact same physical properties and put them into a single space because they clash with each other. And so what I would say is that makes a lot of sense in context of the electron being the surface motion of an atom. As you add more motion to the surface of the atom, you're going to have to be careful to add it in such a way that it is harmonic and supportive of the motion that already exists there, because otherwise it's going to be far too difficult for you to add onto it. It's going to take too much energy. And so if you take the electron, which is the surface of the atom, to have a specific motion, then it makes sense that you wouldn't be able to just add any kind of motion to it willy-nilly, because there's already so much momentum there, because it's part of this vortex of the atom, that the electron that you add to it is then forcibly changed by that existing motion in order to fold into it. Does that make sense?
I mean, I think we have to be really careful too. These are not material bodies, these things with,
Well, they're fiber that's in motion, and so it is material. It's material body that has some kind of characteristic action, right? Do you think that's fair to say?
I do. I mean, I think it might be worth talking about what it means to shoot electrons or something like that. Because I think there's this misconception that electrons are these little balls that can be thrown across a room. We have electron guns, right? We have cathode ray tubes. And so we have to really pause and reconcile that with the model, because we're saying that you're not actually throwing a piece of the atom at another piece of the atom. So let's talk about these cathode ray tubes for a second.
And that's
Generally speaking,
that's how old TVs were made, right? Like we're all
Yeah.
looking at these flat TFT and LCD screens and whatnot. But back in the day, there was this chemical screen, and in the back there was something, and it would scan across the monitor, and that scanning would be modulated by magnets, I think. But
Yeah.
you explain how these old TVs worked and how does it make sense with your model.
Yeah, exactly. So, this is a nice point of contention, because we're not saying that little pieces of the atom, the electron, are getting thrown off of the atom, which is conventionally how it's described in these guns. You're shooting a little piece of the atom at another another atom. And we're saying, no, that's not what's happening here. And the fundamental misconception stems from the idea that these vacuum tubes are actually vacuums. They aren't. They actually have inert gas in them. They have rarefied gas. They're under negative pressure for sure. They've been evacuated, but there's still quite a few atoms bouncing around inside of those chambers. Now, what we're proposing happens during this event where you're shooting an electron is what you're doing is you're actually applying a current across those rarefied atoms in between the emitter and the detector, let's say the gun and the screen in your TV. What you're actually doing is you're forming something like a lightning bolt, where you're organizing and stretching those atoms. Their shells are getting stretched under the tension of that vacuum. And you're actually arcing a current, just like a little wire, between the back and the front of that TV. You're actually making a column of atoms where their shells can conduct electricity, just like we've described previously, which is this shell-to-shell interaction of whirling up the next atom in line. And so you have actual little lightning bolts that are being manipulated with magnets, like you said, because you can manipulate atoms that are spinning, because they have magnetic character. You can force them into different lines, and you can direct where that lightning bolt is going, essentially. And so we're not saying that the electrons are getting thrown from the gun to the detector. We're saying that the atoms, the rarefied gaseous atoms in between, are being ionized and transmitting the electricity in a controlled fashion to the back of the screen.
So much of what we do is figure out what the experiments are actually saying, which is actually kind of fun, because I feel like we're kind of, I don't know, like physics archaeologists sometimes, where you have this concept, fermion versus boson. And in order for us to be able to actually explain what that means materially, we have to go in and we have to look at the experiment. We have to figure out how the experiment is constructed that allows you to make the claim. Then we have to go from that experiment into understanding the physical possibilities, and then we can come out the other side with an explanation for the observed effect. And so we haven't done that for fermions and bosons yet, which is probably, I mean, I don't want to say it's an oversight because we're still so early in this, but I think that you've given us a really good topic for one of our next videos on this channel, because I think that that would be a really, really powerful thing to be able to lay out very clearly. And so we'll have a better answer for you very soon.
I mean, in terms of the spin symmetry and so forth, it does make sense though, right? All of the electrical properties make sense in the context of this involuting shell, which has this unique SU2 spin 1/2 symmetry. A photon being spin 1 makes perfect sense, because of course this wave can be rotated like 360 degrees and get back to its original place. Like that makes perfect sense. So everything that we learn about the model does slot nicely into these symmetries.
But it's the specifics of the language that I think is what's desirable. Because I think that when we talk to people and people come up through the language of fermions and bosons and the Pauli exclusion principle and all of these very standard quantum explanations, it's just satisfying to be able to take those ideas and to very, very clearly lay out in the specifics of it. Because it's one thing to say something that's general and to say, I'm sure that there is a material explanation and this is probably what it looks like, which is, I think that what you're saying, like at a 30,000 foot view, it fits together. But then the most tantalizing thing for me is to be able to go into the specifics and say, not only does it fit at the 30,000 foot view, but it also fits in all of these different places, and these things come together to give you a more complete picture of what's actually happening.
Yeah, like I think we'd have to go back and tear apart the primary literature that proposes this boson stacking and be like, well, what are they doing here?
Yeah.
And how can we materially make sense of that?
But we will. And so that's a really good point. So thank you.
Yeah. Also, exactly what you're saying right now. I think much of this has to do with linguistics. There's this meme that I saw recently where there's like this really thick book and a really thin book next to it. And the thick book said philosophy, and the other one said philosophy without linguistic confusion. And I was reminded of that also when you explained to me how you think of mass and inertia and those things, right? Like that's a lot of words to really describe the same thing. And to me, that's also why it makes so much sense, and why there's almost I'm at a loss of words still for the sense that I've just made. Like once the sense has trickled through me, and my I don't know language center of the brain catches up, and somehow I'm able to articulate that, I think we'll be good. And then I guess that's why also there's an appeal to like the standard model of particle physics, because if we all have different vocabulary and different understandings, we're going to have these fundamental discussions each and every time. But if we can already agree, okay, hey, this is what's going on, and that's how it helps us. And of course, that's the whole point behind models as well. And yeah, I think as we've gone through history, there were always paradigm shifts in the model. And I really believe in your model. I think that there's so much there, and yeah, that can really move us forward and help us out to think of things differently, explain them more simply. And then once you have that new generation that just kind of learns that as the default, if they don't have the kind of wrong picture in their minds anymore, there's a lot of cool things that can happen from that as well.
And that's why I'm so grateful that you're willing to do this with us, because I think learning how to talk about these difficult concepts is no small task. And that's why we've just been putting out these conversations on that channel. That's really the main point of having that channel, is a sandbox for learning how to talk about these ideas, which are kind of fuzzy when you first have them. And being able to communicate is everything in science. That's what science is. Like, it's theories are dime a dozen. If you can't communicate your theory and make it useful and accessible to people, it's worthless. And people don't seem to understand that. They're like, I should get a Nobel Prize for my idea. And it's like, well, if you haven't found a way to make that idea accessible to people, then no, you shouldn't, because that's the people who are really revered in science, is the people who can take ideas and communicate them to other people and make them useful. And so every time that I have a conversation with somebody like you who's interested in understanding these things, I'm learning new ways to explain things in a way that's more effective. And that's like the most valuable thing in the world. That's why we're writing a book, so we can go out and talk about this with people, go on podcasts, like really learn how to do this better and make it a usable format for people to address physical problems.
And to see the places where there are gaps. Like we
Absolutely.
know that we're missing stuff about the nucleus. We know that we're missing pieces of the model in terms of a complete picture of all of the different questions. And the only way that we can refine it is by having conversations with people who are like, well, what about this thing? And we have yet to come up against something that we can't explain with the model. Sometimes it takes a while. Sometimes it's very painful.
Very
Sometimes
painful.
sometimes there's a lot of like
Sometimes it
long
ruins
dark
our week.
nights. Yeah. But it just, at the end of the day, there's always some kind of explanation that feels like pieces clicking together. And so that feeling that you had about inertia and gravity is the same feeling that we get every time that we explain something. And the fact that you got that feeling about inertia and gravity makes me feel like we're better at explaining what we mean when we talk about those things than about the other stuff. Because every time that we come to a conclusion that fits, we should be able to communicate that same sense of, whoa, that is wild, to the person who's listening. And so
that's kind of why we started with that first book's going to be about light and gravity. Those are the things we understand the best, that we can fold all of the empirical data into. We can explain the most spookiness most confidently about those things. We're going to move from that into electromagnetism, which is even more nuanced and requires even more depth to it. And then eventually we'll get to the nucleus too, which is, of course, the final frontier, even for mainstream scientists in terms of understanding that. So it's kind of this iterative process of refining those understandings and then moving into more and more fresh territory and making sense of it. But I mean, honestly, conversations where it's at for me. It's like I never learn more than when I'm talking to somebody who knows nothing about what I'm talking about. And I'm having to explain simple things and coming up with revelations about my own understanding, gaps in my own understanding. And so it's like extremely super duper valuable to have you here to talk about these things.
Agreed. Definitely.
It's also really interesting for me to see how both of you have a different style of explaining and how I kind of get a different perspective about the same thing, but with a different vibe to it. And
I appreciate that, because at one point I think that you accused us of being the same person.
I mean, when I first started this too, I was like trying to get Anastasia to get involved in this project, and she was like, what do I have to bring to the table? And I'm like, no, like, you're super important here. Like, you have a way of seeing when I'm not communicating something properly. And honestly, as the years have worn on, Anastasia is solving problems herself, and it's like she's come up with a lot of the modeling that we have today. But it was kind of difficult to pull you in originally.
What can I say?
Yeah, I love the harmony between you two, and like how you. I think sometimes of leader-follower dynamics, and it's funny how you lead and follow each other when necessary. You pick each other up where it's needed, and it's just a great compliment. I love to see that kind of compatibility and chemistry. It's really cool, and especially if it is something that has potential to change the world, like even better, even crazier. That's really cool.
I really appreciate that.
Yeah, thanks, man. And yeah, thanks for giving us your time and all the time you've given us so far. I know you're a very busy man, and yeah, it means a lot to me. So thank you.
We should return the favor and do an episode about Enolve.
I'd appreciate that.
Yeah, like when you're ready to talk about, if you're already ready to talk about it, we can get it in the calendar, and like we could put you on the main podcast and then just kind of talk about problems and problem solving and figuring out how to run a world-changing enterprise. I think that would be really
Let's
fun.
do it sometime. I'm in the process right now of kind of, like I was saying when we got on here, I'm in the process of putting the right paywalls in place to make sure that we can kind of fund this venture. Because I was thinking about as you guys are talking, right? There is scientists right now who have like apparently enough budget to at least build a Large Hadron Collider and stuff like that, right? So there are working scientists, and I don't think it's nobody's saying that scientists are getting rich or something or hoarding all the resources or whatever, but there is, it is work that's happening. And yeah, as we all kind of do that work, like I think figuring out how to distribute those resources to make sure that there is useful stuff coming out. And, like, is it useful to have, like Michael was saying, that periodic system of the elements, but except for, subatomic particles? Is that a useful thing? Can it help us out? Was that worth spending millions or billions of dollars on that? it's kind of hard to say, right? So that whole thing is interesting of how to fund research. And a similar thing happens in startups where there's venture capitalists who will give money to ideas, but only if they can kind of see that the people behind the idea are actually competent enough to pull it off and make it happen. And then sometimes it's about timing and market conditions and how much traction you can get. And so I think that's also where our situations are a little similar, where we find ourselves in positions where we have to market our thing to get it out there, and we have to convey the value of it to the rest of society so that we can continue doing what we're doing and actually like feed ourselves and whatnot. And I think that's perhaps a challenging thing for like visionaries, because that's, as you were saying earlier too, Michael was talking and Anastasia were saying, I was really busy visualizing very hard. I think that's perhaps what makes people like ourselves, who we might be, that not everybody has this ability or willingness to visualize like that. They're good at other things, but this visualizing and creating these models and concepts in our minds, there is some value that it adds to society, but not in the same way that, let's say, building a house does, right? Like if I visualize a house, nobody can live in it. It still needs to be built. It still needs to get out there.
The unfortunate truth, yeah.
Yeah, it's kind of the tragedy of being an imaginative person, let's say an artist or creator of some sort, is that that's all you care about. And it's very, very hard to make yourself care about feeding yourself or making sure that you reach lots of people or whatever. Those are things that don't interest artists fundamentally. And so hammering yourself in, like forging the discipline necessary to actually succeed as an artist, is something that very few people are capable of forcing themselves into.
But I like the idea that Oliver's working at Enolve, which is that if you want to build a house but you don't know where to start, then this is a way to organize yourself into figuring out how to solve the problem that you don't have a house. Right? Because I think that the more that I think about it, the more that I see it as kind of offshoring executive function. Right? Because somebody who's really, really high functioning and is just super high proof might not need Enolve to go through the process. But what you're doing is you're democratizing it so that somebody who doesn't have that ability inherently and intuitively and natively can leverage technology and the community in order to get it for themselves.
The best thing for an artist to do would be to grow a good network of friends that are very different from themselves, because they're never going to be the best marketers. They're never going to be the best business people. That's not if you're a good artist, you're obsessed with the creative process, and that's where all of your energy is going. So forming those connections and being able to work with other people in easier ways is absolutely essential to succeeding in the modern world as an artist or a creator, a thinker, an inventor, whatever, a startup.
Also, if you speak of artists, every artist has an instrument, or, we all have these tools. And to me, that's kind of fundamental to being a human, that we've built these tools that help us become who we are today, that we're sitting here speaking into microphone thingies and see each other, even though we're miles apart, right? That software that makes it happen is a very conceptual tool. It is highly abstract, and few people actually understand how does it work that you can hear me right now. Like if we had to go through that, right? And you are developing a model that helps us visualize how to think through that, and then who knows what kind of technologies we can build off it. So that's where our idea is worthless, or idea is everything that has any value at all. It's difficult to draw the line there.
That sounds like a killer title
For our next conversation?
For our next conversation, yeah. Are ideas worthless, or are they the most valuable thing of all?
Intriguing question. Thank you so much for letting me pick your brains too. And I gone through my list of questions here, and I'm glad we were able to come up against some things where it's maybe there's still room for development, but also the things that you have developed already are just that feeling of making sense. It's like to me it feels like it kind of puts you a little bit ahead too, right? Because whenever we study things, we want to make sure that we kind of fend for ourselves and whatnot. And like, oh, I figured it out. I can finally relax because I understand it now. It's all good. And so it's kind of that upgrade in competence, in mental ease. Feels great.
That's fantastic. That's really good news. Yeah, let's do it again soon, man.
Excellent.
Excellent. Well, have a good rest of your day.
Yeah,
You
have a
too.
good workout.
Thanks again, and keep up the good work.
Thank you for everything, Oliver.
See you later.
See you, dude.
Bye.
Bye.
Bye, everybody.